Okay, so today we will talk about something called optimization. Optimization is a powerful technique to maximize, something in practice, your profit, the area of something. You're interested in finding the dimensions of a box that have the right properties. And as it turns out, you can use calculus for a lot of these things. So they're very useful. You want to make a bridge. You want to minimize how much steel you want to use for your bridge. If you know physics and you know calculus, you can figure out what's the best way to save on steel. Okay? So this is all heading into that direction. If you're an engineer or an economist, you're going to be using this a lot. All right, so then, and today is already December. Who would have thought? This is 4.7 optimization. Okay, as I said, special type of problem. It's actually a word problem. So part of the problem really is to understand what you're being asked. And it's usually reduces to finding the absolute minimum or maximum of the proper function. So you say, well, this is just min-max. But no, the problem is you need to find the function. That's really the most difficult part for these problems, is to finding what function you're supposed to maximize or minimize, and what are the variables. So what the book recommends, the book actually has a whole list of things. Maybe I can flash it to you guys. It says, I don't know if you can read this here. It says, first understand the problem. Can you read here? Yeah, it's pretty clear, right? Anyway, let me make it even bigger. Okay, so understand the problem. The first step is to read the problem carefully until it's clearly understood. So because you look at the problem, you find out, okay, so how exactly does this look like? What am I supposed to optimize? Then draw a diagram. In most problems, you're supposed to draw a diagram, unless it's really not applicable. Unless it's a completely algebraic problem, you don't need to draw a diagram. But if it's anything other than a completely obviously algebraic problem, you really are encouraged to draw a diagram. Then the book suggests to introduce the right notation. Sorry. There you go. Okay, so introduce the right notation, right? So call things the right way so that you know what it is that you're supposed to optimize and what it is that you're free to change. For example, if you're looking at the dimensions of a box, you'll see in a moment, there's different variables. So you have to give names to things. And then in the end, you really have to get rid of all the variables except for one. So you can optimize this one variable. All right, expressed. This is probably too much information. Use the equations to eliminate all but one of the variables. So the function, whatever you want to optimize, will be expressed as a function of just one variable x. So q equals f of x. Write the main multifunction and use the methods of the sections on maxima and minima to find the absolute minimum or maximum value of f. All right. So I don't want to dwell too long on this without actually telling you an example. So let me give you a specific example of optimization problem. Okay, so example. Actually, let me write very quickly here. my own short version of this. Read and understand the problem. Second is to introduce notation. Write as a function of a single variable Sometimes what you want to optimize is a function of multiple things. You have to get rid of them. We'll talk about that in a moment. And then find the absolute minimum or maximum. All right. So, example. Let's see. The sum of two positive numbers is 10. Find the largest possible product of these numbers. Okay, so you got two numbers, you add them up and they give you equal to 10. Question, what is the largest possible product? So for example, if you want to understand this problem, I would, for example, take some two numbers that add up to 10. For example, 8 plus 2 is equal to 10. And the product is 8 times 2, which is 16. We can also take two numbers such as 6 and 4, which also give equal to 10. And the product, 6 times 4, is 24. What about if I do go all the way? Let's say 1 plus 9 is equal to 10. The product is 1 times 9 is equal to 9. So as you can see, there's a whole bunch of ways to choose the two numbers that give you different products. And we want to find the maximum possible product. Okay, so this is the first step, is to try and understand the problem as much as possible. The largest product we found here is 24. Do you think there's anything bigger than that?
Yeah, 25.
Okay, so keep your thoughts to yourself for now, or think about what could be the best possible product without telling your neighbors, and then and we'll see if that works out. Okay. So suppose that we already understood this. In this case, is this an example of a simple problem that I'm not sure really how you would draw a diagram of this. I think in the really 95% of the cases you will be able to draw a diagram. In this case, we really have just the two numbers. There's no need to draw a diagram. And now, I hope that you guys have some suspect combination of numbers that give you the maximum possible product. And let's see if the hunch is correct. Okay? So, suppose that the two numbers are called x plus y equal to 10. Okay, so we're going to call the two numbers x and y. Here we're introducing notation. Actually, this is 2, sorry. Okay, and write as a function of a single variable. Write as a function of a single variable. Well, the product, p, is what we want to optimize, is equal to x times y, right? Is p a function of a single variable? No, right? It's a function of two variables. So we somehow need to get rid of that other variable. Let's say that we want to write everything in terms of x. And we're writing it in terms of x and y. We cannot optimize two variables. We really need to boil it down to two variables, to one variable. So how do we get rid of, for example, of y? Yes, sir? Move x to the other side. Okay. So from here, I know that y is equal to 10 minus x. That's right. So now I have written y in terms of x. That means that p is equal to x times 10 minus x. That's really the main idea in any other optimization problem. First, write down whatever you want to optimize as p as a function of whatever other variables, and then get rid of the other variables so that everything is in terms of just one variable. P is equal to x times 10 minus x. And now 3 is to find the absolute minimum and maximum of that function. By the way, what is the least possible value of x? Least possible value of x? No, the least possible value of x. What is the smallest that x can be?
0.
0, that's right. Well, actually, we said that x and y are two positive numbers, so really x has to be strictly larger than 0. But let's say bigger or equal than 0. And what is the largest possible value that x can have?
10.
It's 10. Because when x is 10, y is 0. If x is anything bigger than 10, y would be negative, right? Okay, great. So now we're optimizing a function p, which is a perfectly smooth, nice function, on a closed interval. The reason I didn't want to include 0 and 10 in the statement is because if x is equal to 0, the product is 0. Okay? If x is equal to 10, the product is 0 too. But actually that's okay. We can throw them in. We know they're not the answer, right? Because they're not going to give you the maximum product. But we can throw them in. When we optimize in this continuous function on a closed interval, we have a lot of tools to do this. What is the main tool to optimize a function on a closed interval? What is the first thing you can think about when you want to optimize this function on a closed interval? Is to derivate and set equal to 0. That's right. So let's see. So p of x is equal to, we could derive it here, but actually I would suggest multiplying out first. 10x minus x squared. Why do I multiply out? Because the derivative is easier to calculate that way. Now we can calculate p prime of x is equal to 10 minus 2x. And we set it equal to 0. So that means that 10 is equal to 2x, or 5 equal to x. Aha. So some of you are like, well, we already knew that. That's obvious. You know, you plug in 5, you get the product is 25, right? Well, actually, it's not so obvious. You might have a hunch that 5 is the maximum or the optimal number, but this is a proof. Okay, here we're actually proving that that's the answer. So who was thinking that 5 was the optimum number? 5 plus 5. Great, awesome. You guys are thinking just the right way. So it's ideal if you know the answer beforehand, or at least you know a hunch for the answer, and then you prove it. That's perfect. So that means that x is equal to 5, and p is equal to 5 times 10 minus 5, which is 25. So even better than 24. Not only that, but we actually know this is the maximum. How do we know this is the maximum? Right now, I just derivated set equal to 0. How do I know for sure that's the maximum? Well, the fine point of this optimization or maximization algorithm is the critical points are points where the derivative is 0 or the function is not differentiable. Are there any points in this parabola where the function is not differentiable? No, right? Perfectly smooth function. No point where p prime does not exist. So I don't need to worry about those points. And also, p of 0 is equal to p of 10 is equal to 0. That's not the maximum. The endpoints, 0 and 10, are the other possible suspect points for maxima and minima. When you're maximizing a function, you're supposed to look at the endpoints. But the endpoints here are obviously not maximum and minimum. So really the only point left is that point where the derivative is 0. Okay? Great. So that's the answer. Actually, that's not quite the answer. The answer is, this is the largest product. All right, great. Now let's do a problem where we actually need to calculate, to draw a diagram. So example, let's see. A cardboard box has square base. Square base and no lid. And its total area is 12 foot square. Find the dimensions that maximize the volume. Okay, so let's think about it. We have a cardboard box. Cardboard box is a box, right? It's made out of cardboard and it has no lid. So it's really only the sides and the floor. Okay? No lid. Moreover, you know that it has a square base. So let's think about possible scenarios. We can have a pretty tall box. Okay? Remember, no lid. No lid. Okay, so it's really only the bottom part. And we know that the bottom is square. So whatever this is, let's say x. Let's say x is here. And we're going to call the height h. Now notice that I'm using the same variable for this side as for this side. Why can I get away with saying that this side is equal to that side? Why not like x and y? Because the base is squared. So here I'm using the information that the base is square. Okay. Now, what is the area? Well, actually, let me say something else first. Let's suppose that the area of this thing is 12 foot squared. Okay? Is this really the only configuration I could have for a box with a square base and no lid that has this area? What other way could I have to do the same? Well, I could actually have a wide and narrow box like this. That also has a square base and also has a equals 12. You see, I actually have some leeway. I can make many different boxes that have area 12 square feet and a square base. I can make it tall and narrow. Sorry, I can make it tall and narrow, or I can make it shallow and wide. In both cases, the area, the total area, will be about 12 square feet. Okay, so do you guys now see from this problem, do you understand how you can make different boxes that have the same area? But they probably have different volumes, right? So the question is, how do we optimize the shape of this thing? Is it going to be tall and narrow? Is it going to be shallow and wide, or what? Okay, so let's put some numbers in here. What is the total area of the box? Total area meaning the sum of all the sides that are being used. Remember, it has no lid, so it's only the 4 sides and the bottom, right? Okay, what is the total area? Well, let's say it's the bottom. Bottom has area x squared. That's the bottom of the box, plus the sides. Each of the sides has area x times h, right? And how many of them are there? 4. So 4 times x times h, where each of those things are the sides. Great. That's the area. Do you guys agree? If it had a lid, then this would be 2 times x squared plus 4xy times h. Okay, now what is the volume of this box? The volume is x squared times h. Great. Right? So now we have the area and the volume. But remember, so this is what we want to optimize, is the volume. But remember we said write as a function of a single variable. And right now the volume is a function of 2 variables, x and h. So how can I get rid of one of the variables? Let's say leave everything in terms of x. What do you think? What do you think? How do I write the volume in terms of only x? Sorry?
Move the volume, the x on the right side to the left side? Or the x
Move the x where?
Move the h to the left side, like divide by h.
Okay, so basically solve for h. In what equation?
The second one? Or no, the first one. You want to know the
What equation? The one for the area or the one for the volume?
area one, so the volume one.
Okay, so you have the right idea. The idea is to solve for h in terms of x so that you can write, everything in terms of only x. We solve for x in the volume equation or in the area equation? We solve for x in the area equation, of course. The volume is variable. We want to optimize the volume. That's the function we want to write down in the end. So we want to write h in terms of x in that function, so we solve for h in the other equation. Okay, so solve for h, x squared plus 4xh is equal to, and here we use the information that the area is 12 foot square. Okay, so x squared plus 4xh is equal to 12, and we want to solve for h here. So 4xh is equal to 12 minus x squared, or h is equal to 12 minus x squared divided by 4x. Great. So now that we have h in terms of x, we can write the volume of the box as a function of x. Is x squared times 12 minus x squared divided by 4x. Right? That was h. This thing was h. But now I write everything in terms of x. I'm going to simplify this a little bit just for kicks, because after all, I'm going to be derivating very soon. This is 1/4 x times 12 minus x squared. And this is the same thing as, let's multiply it out. It's 1/4 times x times 12, which is 3x minus 1/4 x times x squared is 1/4 x to the 3. Okay, fantastic. So this is v of x. That was what step was that? This was all step 2. This was step 1. Make a diagram. Step 2 was introducing notation and writing everything in terms of one variable. And now step 3 is to actually optimize for this function. What is the... Okay, let's for now, let's calculate the derivative of this thing and find out what could be the potential maximum. So once again, the derivative is 3 minus 1/4 times 3 x squared. We set this equal to 0. That means that 3 is equal to 1/4 times 3x squared. So I cancel out the 3 on both sides and I multiply by 4 and I get 4 is equal to x squared. And so 2 is equal to x. Why? I mean, in principle, you have another solution which is -2, right? Why am I not writing -2? Can anybody tell me? Why not -2? Why not -2?
Because -2 is not a measurement.
-2 is not a measurement, that's right. You're going to be hard-pressed to find a box that has side equal to -2. That'll be pretty hard, right? Right. So then we keep to the positive values of those boxes. Okay, let's look at the fine print. No points. V is a nice function that has no points, where V prime does not exist. What about the endpoints? What about the endpoints? We didn't even say what is the maximum and the smallest value of x. What is the smallest, if you really push it, what is the smallest possible value of x? 0, basically, right? You can make a box that is 0 and really, really tall. I mean, you could not really make that box, but you can make it as small as you want. So let's say that you could, so really x is actually bigger than 0, okay? Okay, so it's really bigger than 0, but for 0, the volume is 0. So let's throw that point in. What is the maximum value for x? Let's think about it. Let's think about it. H is equal to 12 minus x squared divided by 4x. So h has to be a positive number. There's actually an x that's so large that h becomes 0. What do you think? Okay, so when is x squared equal to 12? So x squared is equal to 12. That means x is equal to square root of 12. Sorry, that's not a very nice number, but it is what it is. What I'm saying is, if x is equal to square root of 12, then h is equal to 0, and the box is basically completely flat, the volume is 0. Right? So the endpoints are not good, because at the endpoints, the volume is 0. And v is equal to 0 at the endpoints. Okay, so basically what I'm trying to say is that the only point that could potentially be the maximum is the point where the derivative is 0, that's this point, 2 equals x. Okay, so now the question is find the dimensions that maximize the volume. So we need to go back and draw the function, draw the box. What is h? If x is equal to 2, h is equal to 12 minus 2 squared divided by 4 times 2 is equal to 8 divided by 8 is equal to 1. So that means that our box looks like this: 2, 2, 1, 1. That's the optimal box. Okay, and it's optimal in the sense that if you make it a little bit taller, the volume is going to go down. If you make the box a little bit more narrow and wider, the volume is going to go down. That it really is the optimal configuration. All right. Still have some time. Let's do another example. Let's see. We're going to do problem 33. So, example. Let's see, the top and bottom margins of a poster are 6 centimeters and the side margins are 4 centimeters. Area of printed material is, and they give a number here. I kind of want to change that number. Okay, no, okay, fine. Let's do this. 384 centimeter squared. Find dimensions of poster with the smallest area. Okay, sorry, my writing is not the best, but I hope you can see this. Okay, once again, you have a poster. Say that you want to make a presentation in a conference, okay? Some undergraduate research conference. You really like to make your poster, let's say, as large as possible. And, well, it's actually the smallest area, so that's not true. Okay, so, all right, fine. You want to go to this conference, you want to carry around the lightest possible poster. Well, they're not that heavy, actually, but anyway, so, all right, so for some reason, I mean, I don't really know why you want to do that, but you want to find the poster with the smallest area. Okay, so let's think about different posters that have this configuration. So one is to make sense of the problem. This is what the poster would look like. Some kind of poster like this. And the restriction that you have is that the top and the bottom and the sides have margins. Okay, so the margins on the side are 4 centimeters. The margins on the top and the bottom are 6 centimeters. Okay? Now, let's say that the side of the actual printed material, which is the inside, is X. And the height of the actual printed material is Y. Okay, so Y goes from here to here. It's just the printed material, not the whole height of the poster. Now, what information are we being given? What exactly is 384 centimeters in terms of these variables? X times Y, that's right. X times Y is 384. Okay? Not the area of the total poster, but just the printed material. Find the dimensions of the poster with the smallest area. So now we're calling something also area, but it's different. It's a different area. In here, they refer to the area of the whole poster, not just the printed material. What is the area of the whole poster? Let's call this A. That's right. So X plus 12 multiplied by, this is the total height of the poster, multiplied by the total width. Oh, sorry, this is Y plus 12. X plus 8. Okay, so this is the total width. This is the total height of the poster. Great. But on the other hand, we know that X times Y is equal to 384. Okay? That means that if we wanted to write this as a function of just X and not Y, what can we do? We can write Y in terms of X. Y is equal to 384 divided by X. And that means that A is equal to 384 divided by X plus 12 multiplied by X plus 8. Okay, great. Have we done 2 here? This is 2. We have written everything in terms of a function, and we have rewritten the function in such a way that there's only one variable left. So do you agree that for different values of X you get a different dimension that satisfies these constraints? Okay, great. So now we optimize this function. Before I optimize this function, maybe let's write it down a little more easily. So A of X is equal to, I'm going to multiply out. So this is 384, this times this is 384, plus 384 times 8 over X, plus 12X plus 12 times 8. Okay, now A prime of X is equal to, and we have to derive it on all sides, and I get minus 8 times 384 over x squared plus 12 times 12. That's it. And when I set equal to 0, I can multiply on both sides. I can add on both sides, and I get 12 is equal to 8 times 384 over x squared, or let's see, so here I can cancel out this turns into a 3, this turns into a 2. X squared is equal to 2 times 384 divided by 3. This is 2 times, what is that? Oh yeah, the whole thing is 256? Okay, sure. I mean, this is 84 is 20. Okay, all right, 256. So the next is what? 16? Great. Thank you, sir. What about minus 16? Same thing as before, you cannot have a negative dimensions, so you only have the positive one. Okay, and that means that y is equal to what? Did you say 34? 24. Okay. All right, that's it. So the total dimensions are let me do this. It's actually a tall poster. So this is 16, this is 24, here are 6 and 6, and here's 4 and 4. That's it. There you go. So in the end, even though there is a fine print, these problems tend to boil down to find the function, derivate and equal to 0, and there's most of the time, or practically always, there's going to be a single point satisfying that constraint. And at that point, you need to think about whether that's the maximum or the minimum. Because remember, the derivative equal to 0 could mean maximum or minimum or neither, right? But the way these problems are set up, usually when a derivative is 0, that is the optimal point. For example, in this case, if you make x very, very large and y very, very small, you're going to get a really, really large total area because there's going to be a lot of margin, right? So this is really the minimum surface area.